In this lecture, we are going to consider the topic capacitors in series and parallel. Before we continue, we are going to look at what we discussed previously, and then we consider capacitors in parallel, capacitors in series, and we also go ahead to solve mathematical problems on capacitors in parallel and in series. Let's get started. So previously, we had defined capacitors, considered uses and applications of capacitors, considered capacitance of a capacitor in terms of definition and solve problems. We had that Q equals to CV, where Q is the charge on the capacitor, C is the capacitance, and V is the potential difference on the capacitor. If we make C the subject, then we have a new expression in equation 2 as well. We also had equation 3 to represent dielectric constant in a medium. We had considered electric field strength as shown in equation 4. We also had another expression for electric field strength, E equals to Q over epsilon naught A. And equation 5 as well, V over D. So if we equate equation 4A and equation 5, we have a new equation as shown here. Assuming we cross multiply, we deduce equation 6. If we turn it upside down or cross multiply as well, we deduce equation 7. In this equation 7, you can see a point Q over V, which represents capacitance of a capacitor. So we had to replace the value Q over the alphabet Q over V with alphabet C in equation 8. So this was the expression we used in solving all the problems we considered. So if you have not watched the first part of this topic, I would advise you just go and look at it, because I know you will learn other new things in that topic. Okay, so we also had that the charge Q equals to the product of area and the surface charge density. So if we make the surface charge density in equation 9 the subject, we would always generate equation 10. Capacitors in parallel and series. For a capacitor in parallel, to obtain the equivalent capacitance, we use the expression Ct equals to C1 plus C2 plus C3. So look at the figure below. You can see that this figure represents capacitors in parallel. And if assuming you have capacitors as arranged in this figure, 3 of them, then you use equation 1. Assuming they are 2, then we will take off the last value of capacitance, and then we use Ct equals to C1 plus C2. Assuming they were up to 4 being arranged in parallel as shown, then we will use C1 plus C2 plus C3 plus C4 as well. But the sentence here says that if we have capacitors in parallel and we are asked to find the equivalent capacitance, then we use this expression. So please note it. The expression for capacitors in parallel is not the same as the one in series. So let's look at this other one. It says for a capacitor in series, to obtain equivalent capacitance, we use the expression 1 over Ct equals to 1 over Ct1 plus 1 over Ct2 plus 1 over Ct3 for an arrangement of this nature. So I would like us to look at the figure so we can distinguish between a series arrangement and a parallel arrangement. The resultant or equivalent capacitance of capacitor of any number of capacitors connected in parallel is the sum of their individual capacitances. The reciprocal of the equivalent capacitance of any number of capacitors connected in series is the sum of the reciprocal of the individual capacitances. Anyway, do not bother. The sentence there is simply referring to the capacitor in parallel and in series, which we have already shown here in equation 1 and 2. We have capacitor being arranged in parallel as it is shown here. You now see that to obtain equivalent capacitance, you have to add all of them together. And in terms of capacitors in series, to obtain equivalent capacitor, you have to consider their reciprocal. Let's move on so we can go ahead and solve some mathematical problems. Example 1. The first example here says, two capacitors of capacitances 5 microfarad and 3 microfarad are connected in series. I have shown you a picture of a series arrangement of a capacitor. So it is left for you to be able to memorize it. And assuming you see a problem being given, maybe they just give you the diagram, you should be able to know what to do in a situation like that. But in this case, this example comes with a series arrangement. So let's look at it again. Two capacitors of capacitances 5 microfarad and 3 microfarad are connected in series, and the resulting combination is connected across a 700 volts. What is I? The equivalent capacitance of the combination, total charge on the combination. So we have to find the equivalent capacitance and then total charge on the combination. So before we continue, we are going to, I think we need a sketch. So this is what we have. This is series arrangement and is being connected to 700 volts. So in this figure, one would link this up to where you have the supply, something like this. So this is about 700 volts. We don't have space here, but I want you to see if we are not using this very shape, because this for a battery, you can use it for maybe use a different symbol as well. But let me ignore that because it's not really necessary for now. Okay. We pick an expression as shown in equation 2. But look at this. You have two capacitors here. So we are going to lift the third one, the one that comes with C3. We are going to remove this. When we remove that, this expression reduces to 1 over Ct equals to 1 over C1 plus 1 over C2. We were asked to find the equivalent capacitance of the combination. So we are going to substitute the given values. Don't forget the conversion microfarad, which we have considered here. This microfarad here, remember it means 10 to the power minus 6. Alright, so at this point here, we are to find the LCM. If we find the LCM of 5 and 3, I believe you still remember how to find LCM. If we find LCM of 5 and 3, we obtain the next step here. Let me do it this way. Let's assume, looking at the denominator, we have the value here, 5 and 3. 5 and 3. Pick a number, let's say 3 can divide 3 here, but cannot divide 5, so we bring 5 down. 3 goes here, 1. What is left? 5. 5 comes here. 5 into 5, 1. We bring down 1. So what we have here is 3 and 5. So 3 times 5 will always give us the LCM. So that's what we are going to do here. And of course, if we have 1 over Ct equals to the LCM here is 15. 15 divided by 5 here will give us 3. 3 times 1 is 3 here. Look at this symbol here, bring it here, plus. 15 divided by 3 here will give us 5. I put it here. Okay, so we have 3 plus 5 all over 15, which if we go ahead to simplify, we would have 8 over 15. Alright, so look at it carefully because I'm going to erase it. So whatever you see, you shouldn't be confused about it. Is that clear? So that's how we got 1 over Ct equals to 3 plus 5 over 15 microfarad. You can see we added 3 plus 5, so we had 8 over 15. If we invert it, we turn it upside down, or we cross multiply this expression, we will have Ct, since we are looking for or solving for the equivalent capacitance Ct, so we have Ct equals to 15 over 8 in fraction times 10 to the power minus 6. So this value you're seeing here, what you're seeing here is just more or less saying 15/8 times 10 to the power minus 6 farad. So this micro here represents this value. I just feel I should leave my answer in fraction. I'm not comfortable working with decimal. Doesn't mean that if I convert it to decimal that it's wrong. No, it's still correct. Okay, so we are done with the first one. The next one said the total charge on the combination. Recall that Q equals to CV. So Q represents the charge. We have been able to solve for C, the equivalent capacitance, where we have CT. And we were given in the equation 700 volts, the potential difference. So we are just going to multiply what we have here, and we are going to put in consideration the index 10 to the power minus 6 as well, and then the next one here is the potential difference 700 volts. So when we do that, we will have it at 15/8 microfarad times 700 volts. When we simplify it, we'll get Q equals to 0.0013 coulomb. So that's all for this very equation. If we don't write it in ordinary form, we can write it in index form or the form of indices. Let's consider example 2. Two capacitors of capacitance is 5 microfarad and 3 microfarad are connected in parallel, and the resulting combination is connected across 700 volts. What is the equivalent capacitance of the combination and the total charge on the combination? So looking at this, you see the first one was in series, a series arrangement, but this one is a parallel arrangement of the same equation. Alright, solution. We consider the expression C1 plus C2 plus C3, but in this case, since we have C1 and C2, the expression will reduce to CT equals to C1 plus C2. Substitute the given values of the capacitors. 8 microfarad. I still emphasize 8 microfarad is the same thing as 8 times 10 to the power minus 6 farad. We were to find the equivalent capacitance, which we have done, and the next thing is for us to find the total charge. Find the total charge. You have to think of the expression to use. Q equals CV. Substitute the value for C and the value for V. We arrive at our answer. Example 3. This figure is given. Given the figure above, find the equivalent capacitance for the combination. You look at this figure, you see that C1 and C2 is in parallel. This is a parallel arrangement, and this one is a series arrangement. What are we going to do? We are going to solve this first. When we do that, this will give us a single value. Solving for this in parallel, of course, assuming the answer is 5 microfarad, it means the expression as it is now will reduce to something like this. So it will now give us a series arrangement. So the moment we solve this area where we have the parallel arrangement, this value will give us a single value, let's say 5 microfarad. And of course, we already have 4 microfarad here. So automatically it becomes a series arrangement. So from here, we go ahead and find the equivalent capacitance using the expression for a series arrangement. Okay, so let's go back and then solve it for us to get proper understanding. Consider capacitors in parallel. So we'll first consider the first two capacitors. That's the answer. That will now reduce to capacitors in series, which I have already explained. So if we have solved this and we obtain 5 microfarad, so this is not this complex any longer, but we will have a series arrangement of this nature. So this is 5 microfarad. This one is 4 microfarad. So from here, all we need to do is to use the formula for the series arrangement to solve. And of course, you know that this one is C1 and 2. C1, 2. While this one is C3. So with that, we just go ahead and solve this. We apply the formula, find LCM. You get this. Remember, I had considered this before in terms of finding the LCM. We have 5 and 4. So let's say we have here 5 and 4. Use the lowest term to divide 2 here. 2 cannot into 5. I bring 5 here. 2 into 4 is 2. I bring 2 again. 2 into 5 cannot. I bring down 5. 2 into this 1. I now bring 5 here. 5 into 5, 1. I bring this one down. You now see 2 times 2 is 4. 4 times 5 is 20. So we now use that LCM 20. Write 20 here. Alright, so assuming we use 20 here divided by 5. 20 divided by this 5 here, that gives us 4. 4 times the 1 at the numerator here will give us 4 plus 20 divided by this 4 here is 5. 5 times the 1 at the numerator here will give us 5. So that's how we got the next expression below. So that's how we arrive at this point. When you add 4 and 5, you get 20. Since we are looking for CT, we cross multiply or we just invert it. Then we have 20/9 microfarad. 20/9 microfarad, which is the same thing as 20/9 times 10 to the power minus 6 farad. Example 4. This one says 4 capacitors are connected in series with a battery as shown below. So at the end of the question, you see the figure. Calculate the capacitance of the equivalent capacitor. Compute the charge on the 12 microfarad capacitor. Find the voltage drop across the 12 microfarad capacitor. This is the figure. Since the figure is here, let me take it again. 4 capacitors are connected in series with a battery as shown below. So this is a series arrangement. This is the first capacitor, C1, C2, C3, C4. This is the battery here. Calculate the capacitance of the equivalent capacitor. So in this case, we just pick the expression for equivalent capacitors and then you go ahead and compute that. I believe you should know what to do. Then B here says compute the charge on the 12 microfarad capacitor, and C says find the voltage drop. Let's go ahead. So for the first one, equivalent capacitance, we consider the expression in equation 2, because if you look at this, we have just three capacitors. So we have to add another one because the figure shows that we had up to 4. So we are going to use this expression here. Okay. I believe you know how we got 24. The LCM. So we were able to find the LCM of 3, 6, 12, and 24. LCM of 3, 6, 12, and 24. Okay. I would like you to try that. I wanted to do it, but just try it and see. Okay, so when you do that, you will get this. 8 plus 4 plus 2 plus 1 all over 24. When you add 8 plus 4, you get 12 plus 2, 14 plus 1, 15. Since we are looking for CT, we make CT the subject. So we now have 24/15, which is our final answer. Remember, this symbol here represents 10 to the power minus 6. This symbol here represents 10 to the power minus 6 farad. So I can decide to leave my answer in decimal or as a fraction. I just prefer working with fraction. Okay. The next one said compute the charge on the 12 microfarad capacitor. So you have to note that charge is the same as on the individual capacitors. So if you are asked to find the charge, it's the same across the individual capacitors. So we use the expression Q equals to CTV. Q equals CV. To find the charge is the same across the capacitors, whether it's C1 or C2 or C3 or C4. If you are asked to find the charge on the first capacitor, you still use this expression. The second one, you still use this. The third one, and even the fourth one. So when you do that, you get this. I substitute the value of CT. and then the value of V, and I was able to obtain Q equals to 28.8 microcoulomb as the charge. The next one said find the voltage drop across the 12 microfarad capacitor. The voltage drop, you still use Q equals CV, but in this case we are going to say use the same equation again to find the voltage drop across 12 microfarad. Okay, so Q equals CV, solving for V, which is the voltage drop. Then we make V the subject. In that expression we have Q over C. So the Q has been given here. This is our Q, and I'll put it here. And the C, you now put the 12 here. Okay, remember to observe the micro, this micro column, this micro 10 to the power minus 6. This one has micro here, 10 to the power minus 6 as well. Okay, so the voltage drop, when you divide through, you have this 2.4 volts. It will help me solve other things. So classwork, over which capacitor is the voltage drop the smallest? So what you are going to do is you are going to solve the voltage drop for C1, C2, C3. Okay, I think I've done for C3, C1, C2, and C4. Then you check which of these capacitors have the smallest voltage drop. You now compare and make your comment. Which of the capacitors is the voltage drop the smallest? So that's your classwork. That's what I want you to do now. Then this one will serve as an assignment. A 24 microfarad capacitor is removed from the circuit. This circuit I'm still using now. I decide to remove the 24 microfarad capacitor. So you are going to sketch how it will look like. Leave 3 capacitors in series. Find the equivalent capacitance, the charge on the 6 microfarad capacitor, the voltage drop across the 6 microfarad capacitor. So this same diagram we considered, you are going to remove one of them, the 24 microfarad capacitor, and then use the other ones to solve this example. I would like you to do that now. So you compare your answer with what we have here. If it is the same, then you clap for yourself. Assignment. The plates of the capacitor in vacuum are 10 millimeters apart and 4 meters square in area. Calculate. Let me take this off so you can see. Okay, in area. Alright. Calculate the capacitance, the charge on each plate, the electric field intensity, the electric field intensity in the space between them if the potential difference across the plates is 10,000 volts. So the answer is here. When you do that, when you solve it, check your answer if it is correct. Thank you for watching Supreme Online Lectures. You will see us both on YouTube and Facebook. Please, I would like you to refer us to your friends. Subscribe to our channel if you are yet to do that. If you have done that already, thank you very much. Like and share. Have a wonderful day. Bye.